Hi, everybody. Welcome to the first episode of pH14, a very basic podcast brought to you by the ChemClub at UCSB. My name is Nathan.
My name is Liad.
And today we have with us Professor Brandon Greene.
Hello.
How are you doing today?
Good. How are you all?
Doing well.
Wow.
Yeah, it was a little kerfuffle when we were trying to figure out the mics, but I think we got it pretty okay. So how's your day so far? What have you been up to today?
It's been good. I've been thinking a lot about microphones and recording devices. It's good. Yeah.
Wow, us too. What a coincidence.
The future is bright. I think, future audio engineers and chemists. Great fusion.
For sure. Okay, so I think the first thing we kind of have to ask here, about the mustache. We want to know what grooming products do you use?
Right.
What's your
You're gonna
mustache
hit me with
routine?
that right off the bat. Okay.
Of course.
Yeah.
Yeah, no. So the grooming routine is pretty basic. Maintenance scissors. Puns on puns here. And then, a little beard oil from time to time, but it's not like an everyday thing.
I use the Gillette beard oil, the one where you have like the little dropper.
They're all the same. It's just castor oil or some weird, oil that you could probably get for like a quarter the price, but they mark it up because they call it beard oil.
But it smells good.
Jojoba oil or something. I don't know. Whatever.
I've never heard of those oils, to be honest. Yeah. Tell us about your research. What are you researching here at UCSB?
Yeah, so we are a biochemistry lab. Generally, we study how the microbial world, in particular, we mostly study microbes and how they perform redox reactions, which are really essential to all of life on the planet and also essential for a lot of major industrial chemical processes. So we hope to kind of learn some of the tricks that nature employs to do those reactions efficiently, and then hopefully give those tools to synthetic chemists or process chemists to implement in their work. So we have a bunch of small projects within that umbrella, but that's the main sort of gist of what we're doing.
What's your favorite project in the lab?
Ooh, I don't pick favorites. I'll tell you my favorite grad. No, I'm just kidding. I think, there are projects that are favorites for different things. So there are projects that are my favorite because they're so close to what I've done in the past that I feel very familiar with them and I feel very knowledgeable. And there are others that are some of my favorites because they're so far away from what I'm experienced with that I'm always learning something.
Like what Nathan's doing.
Yeah. Tissue culture was not something I had on my bingo card of career of Brandon Greene's.
Right. Do you find that it's really interesting as a professor, getting that novel perspective again, where you don't know what's going on exactly, or you're not really familiar with something, and you're kind of like a student again?
Yeah, and the really cool thing about that is to see your students, go through that same process together, and oftentimes beat you. It's very cool to see, a student come back after we had a conversation and spend a little time thinking about it and come back with a better idea than I would have come up with.
Mm-hmm.
So that's the really rewarding part of the job is getting to think about new problems all the time and then getting to think about them with other people who are in this emerging moment of becoming better scientists and new scientists.
I feel like it can be hard sometimes though, because a lot of times they might come to you with, expecting guidance and stuff, and you might be just as much at a loss as them. So sometimes they just want you to tell them what to do, but you're also figuring it out with them. So it's just something
For sure. That's definitely the case, but that's kind of part of the process, right? So when you go to grad school, there's oftentimes no more textbook to look at, and there's no, depending on how specific your field is, there's no more expert who knows it any more than you do, right? That you're the one who's just as deeply invested in it as anyone else. And by the time you get your PhD, that's kind of the expectation is that you are the world leader in whatever you do. And hopefully you move away from that and do new things and become, an expert in something new. But also, it takes being vulnerable. It takes being willing to be I'm not the expert on this. Let's do some work. Let's figure things out. And
as a professor, as a grad student?
Both. Yeah, we're both in that journey. I mean, it obviously changes as you progress, and it's the same with undergrads. But as a student progresses, they start with needing a lot more input from me and needing to get some of those initial hints. And then by the end of it, I'm just telling them, what should we do here? What's the next step? And that's when I know it's time for them to go and do cool things, because the apprentice has become the master, so I no longer have anything to contribute. So,
do you feel like there's anyone in the lab that's getting close to that, or not yet?
I won't name names.
Not names, but do you think there is?
Yeah, I do.
Okay.
Yeah.
Cool. That's awesome. Yeah, and I think that as a professor too, with like all your research experience, like even if you're at an unfamiliar project or something, you definitely have like maybe the experience to kind of guide them and say, have you tried this kind of experiment yet? Have you tried something like this? And also just knowing how to look things up in literature is a big skill that people need to know.
Yeah, I think, getting your PhD and spending time in research, listening to talks, listening to other scientists, being immersed in the culture. I often tell my students that getting a PhD is kind of a license to call BS. Like you can listen to something and it may not be in your field, it may not be in you, but you can kind of get a feel for this doesn't sound on a level, this does not sound legit. And that's really like what you're supposed to be learning is like critical thinking, how to critically evaluate just new information and then make decisions on what to do next. So, yeah.
Nice. So do you ever kind of feel like you make it seem more like you know what you're doing because you're trying to give that guidance, but you're also very confused?
Every day and twice on Sundays. Yeah.
Fake it till you make it up.
Yeah, it's a survival skill that you learn in grad school, right? Like, you got to go to this candidacy exam and there's these four, scary professors in front of you and you're saying that, I should be with you too, someday. So yeah, there is that like projection of confidence that I think is important to learn. And part of it is like, if you don't have that, then it's really hard to do experiments that might fail. You have to kind of be able to assume the best and then go into it with the best of, with the hope that it's going to work. And then if it doesn't, and you pick yourself back up. But science is a lot of failures.
Yeah.
So you got to be pretty, ready. And then the other thing is taking, when you don't know something, like not being offended by that, like that's kind of science too, right? Like if you're talking and somebody says like, well, that's actually been known for 30 years. I'm surprised you don't know that. It's like, there's two ways you can respond to that. One is being like, okay, I'm never going to talk again. The other way is you can say, that's a good point. I would not like to be embarrassed by that again. So I'm going to do more diligent literature search, but I also, that's great to know. And I'm glad I am more knowledgeable today than I was yesterday. So.
Has there ever been a moment where you've like talked to another professor who's studying something just like similar, and then they're like, oh yeah, like I've done this like in my lab, or like I know somebody else has been doing this for years, and you're just like, oh well, shit.
Yes. Yeah. And it happened. I mean, we're not perfect, and there's a lot of stuff to keep in your mind.
Yeah.
I mean, I have sometimes a hard time remembering all the details of all the different projects in the lab. So, the literature is vast, the scientific field is vast, and it's better when we don't try to measure who knows more of what and flex on that, rather than come together and try to use the collective knowledge, because it's rare that somebody in the room knows everything that everybody else does and other stuff. It's usually a melding of minds that has the best outcomes.
Yeah, and I guess like you were saying, a lot of it isn't necessarily the pure knowledge itself. It's just the ability to critically think and assess new knowledge. Both of them help. But the critical thinking will, always help you. The knowledge will only help you in context where you have the knowledge, right? So the critical thinking is pretty universal. It's like the old adage of, teach a person to fish rather than give them a fish.
Yeah, definitely. I think so. Like maybe to transition a little bit, how did you get into learning about redox species in bacteria and or just in any organism, and what kind of led you to start researching things like this?
So when I started graduate school, it was kind of like the peak of this climate recognition of, this is an existential thing, and an excitement in the chemical fields about like storing renewable energy. Like we knew about renewable energy, but it was intermittent, and people were realizing that, well, if you actually wanted to do this, you need to store it some way. So I got really interested in how to do that, like how to convert solar energy into chemical energy. And so I ended up working on a project where we were taking light harvesting apparatus. In this case, we were using these quantum dots, or like small little semiconductor nanoparticles that have interesting optical properties. But for us, they were just a way to separate electrons from their home and move them into interesting new catalysts or new places. And what we were trying to do was use that to absorb the energy of the sun, promote an electron into a very high energy state, and then capture that electron with a catalyst that would store it in a chemical bond. And the catalyst that we were using at the time was an enzyme called hydrogenase, which makes hydrogen from protons and electrons. And so hydrogen, obviously a renewable fuel vector, potentially. And so that got me into like studying the enzyme. And then I started getting actually really interested in this enzyme and started looking into some of the microbes that use this enzyme to power their lifestyle. And I was just astonished at how diverse the microbial world is in terms of its ability to extract energy from its environment. And those reactions tend to have a lot of analogy to things that we're interested in doing chemically as just people, as a society. So for instance, there are microbes that can fix nitrogen from the atmosphere, right? We do this by the Haber-Bosch process. It's something like 1% to 2% of the global energy consumption on the planet. And these microbes are just doing it at ambient temperature and pressure and just plugging away in the soil. So I started getting interested in that. And then I kept getting fascinated by new enzymes and kept following those, and it's kind of flourished into my lab. So yeah.
Did you used to experiment with like different types of bacteria, like photosynthetic bacteria versus non-photosynthetic bacteria, how they can either contribute to the hydrogen or just fuel production?
Yeah, so I started as a physical chemist and a laser guy. I started as somebody who wanted to build laser systems and do spectroscopy, and I was cutting much more on that, like,
shout out to Vries.
Yeah, exactly. And so I started there, but then I got more and more interested in the microbial and the enzymes. And so it started as just purified enzymes, no microbe, but enzyme from some microbe. And then it became microbes in my independent career. And we're still primarily enzyme focused in isolation, but we do some work with microbial species. Mm-hmm. But the microbial species we work with is just dictated on the problem we're interested in. So if we were studying photosynthesis, I would want to work with plants and algae, but we're not. Most of the projects that I'm working on now, we're interested in reactions that are only catalyzed by anaerobic microorganisms. So organisms that live in oxygen replete environments, no oxygen around at all. They're very sensitive to oxygen. So that requires us to work in glove boxes a lot, which is not a lot of fun, but the chemistry's cool. So we put up with it. Yeah. So most of them are anaerobes. Without oxygen, the amount of energy you can get from your environment is usually pretty small. And so they're really good at being efficient with the energy they have. And that efficiency, we think, might actually have some implications in how we use energy, particularly electrochemical and chemical energy.
Going back further into like the origin story here, talk about why you found this particular field interesting, why you decided to go into that, but why or when did you decide to pursue science in general and STEM fields?
Yeah, I always liked math and science. From the earliest exposure to it, math always kind of seemed like a little riddle problem to solve, and I liked those. Science was always fascinating because it kind of explained things around me that I thought were curious observations, but then it's like, oh, there's actually an explanation why the sky is blue and why it's like an origin in something. So I was always really attracted to that. And then when I went to undergraduate, pursue my undergraduate education, I basically was like, I like science and I like money. So what is the crosstabs of the degree that gets you the highest amount of money while it's still being a scientist? And that at the time was a chemical engineer. So they were graduating and making, this would sound probably puny in today's terms, but they were averaging making like $70,000 a year out of undergrad.
And this was when?
No, okay. When I was starting would be 2005.
Okay. Try to do the math on what that means in today's currency.
Yeah.
Please don't. So I picked chemical engineering, and I had actually never taken a chemistry class. I just picked it because I was like, well, it makes a lot of money and I'm good at science. I like science, and so I'll do that. And then I took my first chemistry course, and I was like, oh, this is really cool. And I was kind of hooked from day one. And then
and this was an undergrad.
Yeah, as an undergrad. Mm-hmm. And as I proceeded through my undergrad studies, I got more and more hooked on it. And then when I got to like physical chemistry, I was like, oh, this is really cool. And like the quantum stuff just blew my mind. I thought this was amazing. And so by the time I was graduating, I was like committed to graduate school for sure. And I didn't know where that was going to take me afterwards. But I thought being a professor perhaps and doing research long-term would be good. So anyway, I think that was sort of where I found my niche and where I went from there. And then the choice to be a professor was sort of down the line, but yeah.
So you stuck with chemical engineering as your bachelor's?
No, I changed to chemistry. Yeah.
Okay.
Yeah. I changed to full chemistry so I could take all the fun electives that I wanted to.
So do you have a first scientific memory that comes to mind?
That's a good question. Yeah, I think probably my first I don't know if it's a science. I guess it'd be weird how you define that. But one of my earliest memories was my physics professor in high school. There's a name for these. I think they're called a Rydberg tube. But basically, it's a tube filled with natural gas, and they drill holes all throughout it. And then they put a microphone in it, and they play a tune. And if it's resonant with that cavity, you'll see waves in the flame that comes out of it.
Yeah.
And I was just like, oh, okay, that is weird. And that's very cool. And then, explaining, okay, well, sound is a pressure wave. And so there's higher pressure in these areas, and that causes the flame to be higher because there's higher pressure natural gas, and then there's lower pressure in other places. And okay, this is very cool. And so that was probably one of my earliest. All my really, really standout ones were physics demonstrations.
Really?
Surprisingly, yeah. The other one was the holding the bicycle tire on a stool, and seeing the effect of the gyroscope. So yeah, those were always really cool.
I don't think I've ever
tactile experiments.
I don't think I've ever done an experiment like that in one of my schools or one of my classes.
Oh yeah, we had a really good AP physics teacher that was amazing. He was really good. I can't remember his. Well, actually, no, I do remember his name. William Jenkins.
Shout out William Jenkins.
Yeah, shout out William Jenkins.
Where did you do your undergrad?
Washington State University.
Washington State. What kind of undergrad were you? Were you like the studious kind? Were you the work hard, play hard kind?
Yeah, probably more the latter. Yeah. I mean, Washington State is a pretty rowdy school, so I was there for football games on Saturdays, but then I was staying up late on Sundays for the exam on Mondays.
That's pretty good. Do you think that Washington State has a rowdier culture than UCSB?
I would not know.
Anecdotally.
From what you've heard.
Yeah.
I will say that, probably integrated over the year, yes, because of the weather, but I think, for when Washington State gets the weather, they do their fair share of party.
Yeah. I think one thing we don't have is football games, which is like what a lot of schools kind of tack onto.
Yeah.
I don't mind. I prefer soccer anyway.
Yeah. Yeah, the tortillas on the field are great. So what is your favorite undergraduate course that you've ever taken, and why? Or maybe your least favorite?
Quantum.
Least favorite or favorite?
No, that's my favorite.
Oh, okay.
Quantum.
Well, actually, no, I should rephrase. Statistical mechanics was my favorite class because I really liked quantum and I really liked thermodynamics. And then stat mech was like, oh, and then here's how you connect the two.
That's cool.
And that was very cool. And then it was kind of understanding a lot of that was the class where I kind of understood some of the problems that people talk about it, especially physicists, about grand models, things like that can explain all the way from quantum to gravity. It's like, oh yeah, this is a breakdown. Like these equations don't have temperature in them. So how do you get temperature from quantum mechanics? So you just calculate how many states there are, and then that's an approximation of this. And so, yeah, I think that was my favorite class. My least favorite class actually was biochemistry.
And you teach that,
and
now.
I teach that now. And,
oh yeah.
And the reason was because I was a physical chemist. I wanted to be a physical chemist. And so there were no rules. There was no, here's the equation and you'll be able to solve those 9 biochemical problems because you'll know this equation. There are some, but that wasn't the focus. And most people teach biochemistry to the MCAT because the MCAT has certain biochemistry topics that you need to really understand, particularly those that are relevant to human health in particular. So now that I teach it and I get to control what's on the exams, I am much more about foundational concepts. I try to be a little bit more. If you understand these few concepts, you'll be able to solve a lot of different things.
Okay. So speaking of test questions, I think this would be a great time for our little blue book surprise here. We actually brought an old question from one of your classes from a final review.
Great. Okay. Exciting.
So we wanted to see if, just putting you on the spot a little bit.
Okay.
If you'd be able to answer, I guess, paper, pencil.
Do I need to do this?
This might be really easy and will look stupid, or this will be hard.
And
so
other
the question, So the question is, what is the number of ATP required to form activated isoprene units from mevalonate?
Activated isoprene units. Okay. Let's see. 1, 2, 3, 4.
Feel free to draw it out if you want to.
So let's see.
He's doing this all on the top of his head, if you guys can.
Yes, you're losing CO2 every time. So that's your 3 carbons.
Anybody who's taken 142B, the segment's for you.
Yeah, 1, 2, 3.
What is the number of ATP required to form activated isoprene units from mevalonate?
4.
Is that your final answer?
Yeah.
That is incorrect.
What is it?
3.
Did I count for AMP formation?
Show the
Let's see, this is what we have here.
ADP, 3. Okay. I thought you had to make AMP, so then you have to use 2 ATP to get back from AMP to ATP. But I thought there was a pyrophosphate unit, but that's I knew there was 3 steps. I just thought there was a pyrophosphate.
Okay.
I'll
act like I know what that means.
Yeah. when I take that class, I'll figure it out at that point.
Yeah.
All right. Well, I mean, honestly, that was very impressive that you could do that off the top of your head, even if you got it wrong.
Eventually, you sort of. Some of it sticks. I still learn new things every time I teach this class. Every time. And students ask great questions. I mean, I had a student this last year talk about, came in for office hours and we were talking about oxidative phosphorylation, it was amino acid catabolism. And they're like, but I'm really big in the gym and I really like working out. And all the people that work out take this beta alanine. Why do they take beta alanine? And I was like,
makes your skin tingle.
I was like, I don't really know. But then we sat down, we drew out the biochemistry, and we found out that it's kind of the perfect molecule because it gives you nitrogen for making new amino acids. But it also gives you acetyl-CoA for high energy metabolism. So acetyl-CoA is a much higher energy, storage vector and lower weight than glucose. And so it allows for energy recovery and energy in workouts, and then also nitrogen for growing muscle.
Yeah.
And this was without searching anything. You just looked and tried to draw it out yourself.
Yeah, we just were talking. I mean, I don't actually know whether it's the reason why I take it. I don't know if anybody knows. Nutrition is a weird science because it's very pleiotropic, right? Every molecule has 90 different effects, and isolating it down to a clean one is hard. But yeah, that we were just drawing out what can happen, and if you do transamination of beta alanine, all of a sudden you get a acetyl unit and a free nitrogen for making amino acids, and then
Have you tried beta alanine before?
I have not.
Oh, okay. So beta alanine is also the thing that when you put it into pre-workout, it makes your skin tingle and it feels like TV static all over your body. So it's
thank you.
I used to take 3 grams of beta alanine with my caffeine.
You don't have to tell us that. That's fine.
Had to find a reason to talk about your gym routine.
Yeah, it's half of my personality. If you don't know,
the other half is
podcaster.
Being in lab is.
Yeah.
Yeah.
So I guess speaking of nutrition science, I know you mentioned before your interest in molecular gastronomy and nutrition science. So just kind of wondering, well, I guess if you could describe what it is and what drew you towards it, why you think it's interesting.
Yeah, I was never really that interested in food for a long time, but then my wife was in the restaurant industry, and so she kind of introduced me to food. Like through college, I was kind of the person like I could have rice and beans every day, and I was like, I was like, this is just fuel. It's just whatever.
Rice, canned chicken.
Yeah, and so my wife was the one who really pushed me. She's like, oh, this is this is good food, and this is what can happen when people take time and effort and prepare things. And I have a good friend who's a chef, and so all of that kind of exposed me how much that's just applied chemistry. It's just applied chemistry, and it's all on biomolecules, right? Because everything we eat comes from living stuff. You're either eating plants or animals, and so or insects, I guess. But so you're doing chemistry with biomolecules. So as a biochemist, it's very cool to think about how that all plays out. And then I think, it's a growing industry. So I think it used to be that food was kind of considered not like a real career path, but I think it's becoming more and more integrated with chemistry. And I think there's some really exciting new areas of it. Like, for instance, artificial meats and these meat substitutes, and this molecular gastronomy sort of science is what can you do with fermentation and interesting cooking techniques, and then so I started trying to integrate that into a class, and I'm still trying to get that class sort of into the curriculum, but I did it last year as a sort of voluntary class for freshmen.
What's the class called?
The biochemistry of food.
Yeah. Chica, anyone here is an incoming UCSB student. Feel free to check that out.
Chica, if you're listening, put that on gold.
I need to apply, for it to be added to the curriculum. That's one thing though. Our curriculum is it's like moving an aircraft carrier. It's a slow ship to turn around or to adjust from course. So.
If enough students seem interested in it, I'm sure people would love to take it.
Yeah, I think that the trick is that it's probably going to have to be an upper division course because there's not enough space in your schedule to take that at below your sort of junior year, and then it needs to be quantitative enough and challenging enough to be useful for you going forward. It can't just be a feel good. This is fat. Here's some ice cream. Which is kind of what I did with the freshman course. Here's what a fat molecule looks like, and here's McConnell's head of production here to talk about their flavors. So I'm
sure the freshmen loved you though for that.
Yeah. It was 8 a.m. So it was a tough billing, but they did like it. But,
That's good. Yeah, I can't imagine somebody not liking a class like that.
Yeah. We had 24 Blackbirds chocolatier as well in there, and that was cool because I sort of broke the class up into two halves. One half was what are biomolecular structures and what is their property in food, and we use this. Nosrat is her last name, I believe. She has this book. Sorry, that's a timer in my lab. Somebody is inattentive to their experiments. It looks like the beatings will continue. So she wrote this book, Salt, Fat, Acid, Heat, and there's no chemical structures in it whatsoever, but it's this really tactile, salt has this effect and it's chemical, but it's not, there's no chemicals there, So that was kind of the soft intro, and that was technically the textbook. Obviously I didn't require it, so probably none of them bought it, freshmen, but there's a Netflix series too, so they all have Netflix. I'm sure.
Oh really? There's a Netflix series?
Yeah.
Oh, that's cool. What's it called?
Samin Nosrat is, I'm probably butchering the pronunciation, but it's called Salt, Fat, Acid, Heat.
Oh.
And so basically her premise is that if you can master those four concepts, you can cook anything. You can be better at cooking.
Yeah.
So I divided that, salt, fat, and acid, those are just molecules. Those are static structures that have properties in food. Heat, though, is a little different. That changes food. It changes biomolecules, from one form to another after you heat it, right? And fermentation is the same way. So I had it the first half was structure, and then the ultimate manifesting properties, and then the last half was dynamics, like fermentation, which chocolate is a fermented food.
It is?
Yeah, exactly. Yeah, most people don't know this.
Yeah.
But so he brought Oh God.
Does it make it sweeter? Because I know like a cocoa bean is like very bitter.
Yeah, so it's going to contribute all of those weird flavors that chocolate can take on beyond just sugar. So the chocolate itself is very bitter, but it's supplemented with sugar and milk, at various percentages to complement and blend those flavors. So the owner of 24 Blackbirds, and I'm blanking on his last name, Mike something, brought in 2 chocolates that they had made, both 75% cacao, one from Honduras and one from Madagascar. So the exact same recipe, exact same everything, just beans fermented in 2 different places. And they tasted totally different. One was like super citrusy, and the other one was very nutty and sort of rich. So,
and it was the same species exactly.
Yeah, same cacao. It's just what we call like terroir, right? It's like the local, the what's in the plant to begin with, and then what happens in fermentation by the various microbes that are around in that.
Oh wow!
So
that's really interesting.
Yeah, so there's a great book called On Food and Cooking, and it's like the technical Bible. It's like a textbook for food, but it's like this thick, and it's got like the fat percent of every milk from every different or all kinds of different organisms. So like whale fat or whale milk is like 40% fat, whereas like
how do you milk a whale?
Well, baby calf whales milk their mother, because they need milk to survive, and they have a lot of fat that they need to keep warm, and so they have a lot of fat in their milk. Oh, wow. Whereas we don't need that. Babies are chunky, but they're not that fat. And we need a lot more sugar because that's what our brain runs on. So we have a lot more sugar in our milk, in our mother's milk, but we have a lot less fat because we just don't need it.
Yeah, I think one of the things that are that's interesting about food science is also just how you can use it to support human health, right? Like you learn it's not just about calories or even the macromolecules. It's like you have all these things that you need for your body for these different biochemical processes. We learn that your body might not produce on its own, and you need from your diet. But a lot of people just think, if you eat enough and you feel full after, it's like you're good, but your body actually needs these things.
Yeah, and understanding that is, I think, useful for everybody, not necessarily just chemists.
Welcome back to pH14, a very basic podcast where we're here with Brandon Greene.
So before we left off, we were talking a bit about some of the classes you were teaching, the biochemistry series, the freshman seminar class on nutrition science, and we were just wondering, how much do students' opinions about you or their experience with you as a professor in the class matter to you?
Good question. They matter for sure. I take my ESCIs pretty seriously. Like at the end of the quarter, we get evaluations from students, and I try to inform them that if they provide constructive criticism, that I am happy to hear it and modulate with that.
Do a lot of people fill those out?
No, which is unfortunate.
I never feel
like how many people per, let's say, a class of 50 students?
A third to a quarter.
Okay.
It's actually more than I expected. Yeah, it was a lot more than I thought it was going to be too.
Which is not great, because that's part of like how we're evaluated, is how many of those people fill out their ESCI. But that I think is changing. But anyway, it's it's important. I think that as a new professor, I'm still learning how students learn best and what students need. The pandemic has been really weird, though. That I think, especially I taught my first undergrad class the first quarter we were online. So I actually my first year of teaching was all online.
Yeah,
so,
and it also happens to be one of the hardest classes there are here. So.
Yeah, and I tried to do an inverted classroom, so I was pre-recording all my lectures, and having all the stuff that students would do before they come to class, and then when they come to class, we would work on problems that they seemed to be struggling with on all the material that they were doing before class. And so students were like, I have to teach myself. So then the next quarter, I did a lot more teaching in class, and students are like, wow, we like the exercises. So they kind of push and pull in different classes, and different people learn different ways. But definitely, I think student feedback has helped me grow as a teacher. It's not everything. Students are going to complain about having a tough class. That's just kind of the nature of it. And unfortunately, I would like to give everybody A's, but unfortunately, the effort doesn't always match the background. And because those things are anonymous, like every year I get academic misconduct that I have to deal with, and I don't know whether those people are the people that filled out the SKs with the really nasty worst teacher I've ever had or not. But I have to kind of take those things with a grain of salt.
Mm-hmm.
So
for your own sanity, I guess.
yes.
Do you ever look at your Rate My Professor?
I have, yeah. It's not good. But yeah, again, like the same thing goes there, right? It's like I don't know. I think they say like what grade do you expect, or they give something about that, and like I don't remember people feeling like they were going to have a good grade. So it's not like there's a lot of people that got an A that are like, this class was terrible.
Yeah, there were also only like 10 reviews, so again, that's a very small fraction where you don't know what.
I don't know. Do kids even use that these days?
It depends. If it's an established professor that's been here for a while, I kind of am more like serious about it. Like I'm like, okay, then this is probably for over 50.
But do you contribute to it?
Students definitely look at it. I've never contributed to it.
Yeah.
So, because again, it might be those people who had a negative experience that are then motivated to go and write that review. Whereas if you thought the class was fine or you liked it, like you maybe
my glass half full, opinion of it is that it's hopefully a benefit for me now that people come in very scared, very worried, and then they meet me and they say, "Oh, what was everybody talking about? This is a blast. This is fun."
Yeah.
He's really nice. So. Yeah, I don't know. I mean,
so they come in with low expectations.
Exactly. There's nowhere to go but up from I don't know, whatever my rating is, -2 or whatever.
What about in your lab? Like, do you think you have generated a nice lab culture here in your research lab?
It's pretty good. I mean, I think that there, I'm always trying to find new ways to stimulate that. There are some sort of natural lab dynamics that I'm just sort of experiencing, which I'm still learning how to navigate as a leader. Generally, like my experience with everywhere I've ever been is that the closer students are to graduating, the more irritable they become because every experiment's critical. Your time there feels like you've been there for too long. Everybody below you doesn't know as much as you do, and so you feel like you're cleaning up messes from people or you're answering questions that feel silly. And you forget where you were at that stage and how much you needed mentorship. Mm-hmm. And so, there's this young, green, excited new students that come in. And then there's, by the time, it's kind of like the Barbie Oppenheimer memes, you get Barbies coming in first year and Oppenheimer's leaving fifth year, and getting those people to all work together in harmony is sometimes challenging. Obviously, COVID had a big part to play in that as well. That I had, unfortunately, a couple students that really struggled with COVID, and they don't train us as advisors to be psychologists or therapists or emotional support animals or anything. It's you're sort of just left to figure that out on your own, and so that's been challenging to be there for people, but to recognize the limits of what I can do and to try to divert people to resources if it's possible. I wish there was more resources from the university for those issues, but overall, we try to get out once every month or every other month and do something as a group. We have a fair amount of relationship with other labs among the floor, the group's been pretty successful, so I think
that's nice.
It's working.
Yeah. I mean, what was it like starting the lab in general, just starting a lab from scratch, and then especially COVID happening within, a year or so from when you started it?
Yeah, so it was a blast. You're getting brand new equipment coming in, everything's shiny, everything's new, it's clean. Mm-hmm. I was able to be in the lab a lot, which was great. Mm-hmm. And I had a lot of rotation students that were interested in a new lab, so I was, with a bunch of young people that were very excited about science. And so that was really great. And then the lab shutdown was really tough because it was, everybody had to sort of pivot to find something to do. it was time that I was losing, they were losing, everybody was kind of losing. And then we came up with shift schedules that were really, rough. It was like, 8-hour shifts from 7 a.m. or 5 a.m. and then to noon, and then from noon to, 7 or whatever.
Person would just be the only person.
And so, it was like 7 to 2 and then 2 to 10 or something like that.
Wow. Oh my
and
gosh.
so you were allowed to have 2 people or 1 person per 1,000 square feet or something like that, maybe 500 square feet. And so I had 2 people at each time. So you did have one other person, but it was a very disjointed experience for the students. And then rotations were essentially virtual, and nobody could rotate in the lab.
It's awful.
So it was tough, but we came out. We came out the other side, and there's been some natural, I think, ebbs and flows and shakeups in the lab, but hopefully that's settled in, and we're kind of in a cruise control.
Flow state.
Yeah, steady state.
Yeah. Do you think that were you able to publish or do any productive research over COVID, or was it super like a stopcock?
Well, so the research was very slow, partly because I couldn't be here in the lab, or I could be, but it would come at the expense of one of my students. So because of the occupancy rules, I stayed out, I stayed virtual, and I had that time dedicated for my students to do research in the lab. But there's something about being able to show your advisor the bad gel you ran or whatever it is and be like, what happened here in real time, whereas it's like scheduling a Zoom call, it feels like much more formal and like a larger barrier to entry. So that, I think, held up the lab a lot. We did publish some things. So I had some things that had built up from my postdoc that I was able to finalize. And then I also wrote just a perspective, where I think the field is for journal ACS catalysis. There was a lot more work than I thought it was going to be, but it was good. And then we had an invited paper as well that we submitted to Methods in Enzymology. So right now it's sort of in the pickup phase. Now we're starting to publish the things that were started during COVID, and then when people came back into the lab full time, finally are getting up to the level of publication, which is exciting. It's a lot of fun to write papers.
Yeah. So if you didn't have any kind of publication pressure to publish stuff, what would you want to work on? How would that change what you're doing in any way? In terms of the types of projects and things like that?
Not really. I mean, I'm much more of the high quality papers, not quantity of papers. And so this last paper that we just submitted and has been provisionally accepted was my favorite paper I've ever been part of.
Really?
It was
Really?
I'm super proud of it. I think
What was it?
We were studying the mechanism of an enzyme that's involved in anaerobic glycolysis. So it's a common enzyme in anaerobes that allows them to maximize ATP yield from their anaerobic environment. And it's a potential target for things like the gut microbiome, which is anaerobic, and this is connected to central energy metabolism. So we used based on what we thought the mechanism was, we used a molecule that should have intercepted that mechanism and arrested the chemistry, and it did, and we were lucky, and we were able to characterize intermediates and show them by this very fancy technique called electron paramagnetic resonance spectroscopy, and then we did some quantum chemical calculations to rationalize all the results, and it was a very old school biochemical paper, an enzymological paper that is not so much in vogue these days, but my predecessors would have been very excited about it. So it felt
interesting.
good.
I wouldn't have expected quantum chemistry to come up in an enzyme biochemistry paper.
Yeah,
that's cool.
So that is one of the elements. I never lost my physical chemist interest, and so the lab does rely heavily on biophysical techniques and a physical approach to studying biology, which I think is unique among the field, and that helps, I think, a lot of people, at least people like me, get excited about biochemistry because it's some of where the most exciting physical chemistry is coming from, right? The physical chemistry textbooks haven't changed very much from 40 years ago.
Yeah.
What has changed is that we've realized that those concepts that are so simple in the gas phase, when you put them inside a protein that's a asymmetrical, three-dimensional environment, they all of a sudden become weird and hard to predict and much more interesting. And so that's a space that I've enjoyed being and inhabiting.
Right. So what's your workflow? Let's say somebody came to you, like a grad student came to you and he said, well, I found out that my bacteria does this whenever I do this to it. What would be your workflow to kind of like determine what the mechanism is?
Yeah, so most of what we do is isolationist and reductionist. So we try to, if we think there's an enzyme doing something, we try to isolate it and then demonstrate that chemistry in isolation so that we can control as much as we can inside a test tube. So they call this in vitro or in the glass. The more fundamentals thing I would say is that I really try to instill in my students that whatever they do, they design an experiment such that if it fails, they'll learn something. So this is like the art of making controls. So, I did this and I saw the bacteria did this. Okay, well, how can you repeat that experiment and add in layers of new hypothesis-driven experiments that have ways to learn whether they work or not. And so that is very context dependent, and I'm a little bit at a loss of like a good example here, but learning how to design experiments such that you learn something every time makes even a bad day experimentally salvageable, right? It's the really bad days are when you do an experiment and it doesn't work and you don't know why and you have no clue. Then you're really up a creek, and that is not a fun way to go home and make dinner afterwards. So
yeah, I think we've definitely felt that the past few weeks in our projects.
Yeah. Can you think of like a story where you ran an experiment, it failed, and then you either knew why and then it led you to like something that was like a really cool discovery, or like you kind of just kicked the bucket and you're like, okay, scrap the new project?
Yeah. So when I started grad school, as I mentioned, I was working on these interfacing of an enzyme with a light absorbing material that would inject electrons into the enzyme. And we figured that out. We figured out how to make hydrogen from those devices, and so with light, and so we published that. And then I got really interested in the enzyme. So I realized, I said, well, now we have like a new methodology to study the enzyme, because now I can, with light, gate when this enzyme turns on. So with the application of very short laser pulses, so shout out to Matanya number 2, short laser pulses, you can really coherently start the reaction trajectory at a very precise time.
Oh, wow.
So if I have a very short laser pulse that just, a flash for a second, then everything after that is completely synchronized to that laser pulse that I started it with, right? If the chemistry is dependent on the laser pulse, then everything afterwards is all started at the same time point. And so we realized that this was a really cool potential technology for studying the catalytic mechanism of this enzyme, which was under debate at the time. And I spent 3 years trying to get that to work.
Wow.
And so it was a lot of trial and error. And then I had to build the instrument to study what we wanted to see. These enzymes are sort of notorious for having carbon monoxide as a ligand to the active site, which is normally toxic for all of biochemistry, but it's essential for this enzyme. And carbon monoxide is unique in that it has this very characteristic infrared vibrational frequency. And so we developed a technique to transiently follow that carbon monoxide ligand over the course of the reaction. And it turns out it is very sensitive. Its vibrational frequency is very sensitive to what the enzyme is doing. So if you see shifts in that over time, you can correlate that to states and then build a mechanism. And that enzyme actually was a great test case because it turned out to be faster under its optimal conditions than the fastest rapid mixing technique. So like the fastest you can mix 2 solutions, which is normally how chemists start a reaction, is you mix 2 solutions. The fastest you can do that is sort of milliseconds, and this enzyme was able to do things in microseconds. It was able to make hydrogen 10,000 times per second. So the laser pulse thing was critical to doing that. But 3 years of time of failure to get to that point. And then once it hit, it just, we got a bunch of papers out of it. And it was like I could design a paper on, just sketching it out in an afternoon, and I could execute it over a month, and then we'd have it submitted in another month.
Wow, that's awesome.
That's amazing.
So going from 3 years to give me another 3 months and I'll have another paper finished. So
that's crazy. I mean, so did you do anything else for the rest of grad school, or was that sort of the bulk of your work? Like, what was it like in general?
Yeah, so that was
what you worked on.
So basically, the first part was studying how to drive these hydrogenase enzymes with light. Once we figured that out, then we did some mechanistic work on the hydrogenases. So now we take this methodology, we apply it to learn something new about hydrogenases. So I'll brag here, I think we solved the mechanism of this enzyme. And then we moved to a different class of that same enzyme. So it's a different enzyme, does the same function, but it evolved separately. It's not related evolutionarily. And we repeated it there. And the instrument that I built kept on being useful for other systems. So that lab continued to use that instrument that I built. And then also, we learned a fair amount about how these enzymes worked. So yeah, it kind of progressed. It was a couple different things, but the ultimate culmination was we learned something about an enzyme we didn't know before that was interesting and useful.
Did you patent this instrument?
No, I didn't. It wasn't that crazy. It was very cool. I was very proud of it, but it was I didn't feel the urge to patent it.
Yeah, my grad student always says, engineers when you need to be, chemists when you want to be.
Yeah, I mean, well, it's, all chemists are engineers when they have to be, right?
Yeah, it's interesting.
Right. So how did these experiences in grad school in general shape you as a professor or as a person?
Well, I think I learned a lot about the value of long-term commitments towards a end goal and resilience. I also learned, my advisor, who I have very, very high regard for and lots of respect for, he was very much a let you do you, and I'll see you when the results are worthy of my time and energy.
That's great.
And that's good if you're self-motivated, but even if you're self-motivated, you need mentorship sometimes. And my advisor did not, I don't think he very much enjoyed writing, which is actually a really wonderful part of science that if your advisor is enthusiastic about it, becomes a really important part of what you do. And that focus on communicating your results and writing, I think helps you put your mindset the right way when you go into the lab. Like what I want to do today, I should be able to organize coherently into a paper at the end, and being focused like that when you go into the lab really does improve your ability to execute good and smart experiments every day. If you're kind of thinking, I just like science and I'm going to go into the lab, you'll get observations, but they won't be focused, and when you look back, you'll wonder why perhaps they weren't. So that's not how all science needs to be done by any means, but I think that by the time you're getting ready to leave, you should be have the paper in your mind, you're dreaming about it at night, and then you go into the lab and you're very focused.
Yeah, I think in general, it's just important for scientists to be able to communicate their findings and what they're doing to both the rest of the scientific community and beyond that. Scientific communication is a huge, huge thing.
Yeah, so our papers are the first line of that, but then obviously oral communication is a huge part of it as well.
Yeah, being able to explain it well to audiences that might not know as much about it.
Yeah, definitely.
Do you think that's something that the scientific community, maybe at Santa Barbara just as a whole, is very good at, or do you think that they need to work on maybe how they communicate their ideas
to each other and to outside of the community?
Yeah, definitely.
Yeah, I don't think we do much communication outside of our community. I mean, I should say that there might be other departments and other projects around campus that are doing this really well. One thing that I would like to see and that we don't have yet, and that I would love to invest some time and energy to, perhaps after tenure maybe, is a Santa Barbara Science Festival, like a week-long Science Fest where we take advantage of the fact that we have lots of technology here, and we have lots of academics, and we have I think a pretty broad audience of people that would be willing to come into town from the surrounding area as well as Santa Barbara itself, and just talk about science and how it's relevant to modern life and what science involves, what it looks like, kind of humanize it, and then also communicate it to the broader community. But as far as like communicating, I don't know what else is really going on other than small things like, science at the pub. There's like these little things that people spin out.
Sorry, what's science at the pub?
So Science at the Pub was a long-running outreach project hosted by Gab Menard. When he was here, he was part of the chemistry department, or at least it was initiated by Gab, where a scientist would go and give a talk at a local pub, and it was open to the public and advertised at the pub and through other means and on campus. And so then you get an audience there, it's all around beers, and a professor would talk about something and try to give a talk to a lay audience, mm-hmm. and the lay audience could ask questions and see what science was going on in the world.
Yeah.
So that was fun. Sidetrack obviously is a great outreach program,
mm-hmm.
And that's more focused towards K through 12 education and science outreach. That's kind of teaching what the process of science involves, not so much mm-hmm. educating about like scientific facts, but the process of science, like what does that involve. So those are good, but we could always be doing more.
Yeah, I can just totally imagine just drunk people in a pub just being like, oh, so go back to that thing you were saying before.
Yeah. What about aliens?
Yeah. Yeah, do you believe in aliens?
Sure. Yeah, I don't know, why not? I don't know.
have you been following the alien things in the news and the
I don't think any of the evidence that we have is very compelling, but I think it's a lot of space to fill with nothing if it is.
Yeah, definitely.
Yeah.
It's the Russians. It's the Russians.
Yeah.
I mean, so do you think those UFO things they're finding are just advanced human technology that isn't public yet? So people look, they see it and they're like, "Holy shit, this is
mm-hmm.
really advanced." Like
maybe it's also just optical phenomena and hallucinations and
mm-hmm.
just strange things that are explainable by other natural mechanisms. It's tough, but I think that it seems very hard for me to believe that there's evidence of aliens anywhere because, getting even just two people to keep a secret is hard enough. And, getting an agency, especially in the federal government, it's like there's the sort of classic explanation that, like, if it can be explained by stupidity, it's probably explainable by stupidity. And so I think the lack of, any evidence of that is probably a... Yeah.
Okay, so you believe in the possibility, but not in the current evidence that exists.
Yeah, I do.
Yeah, I think this would be a good question for Kevin Plaxco.
yeah, Kevin would be great. Question for that.
Yeah,
for sure.
What do you think about? Because you said you didn't see the Oppenheimer movie, but there are like scenes where they're kind of non-scientists, government officials, kind of like interviewing him, pressing him
mm-hmm.
about what he thought about the different experiments they were running. Like, what do you think is maybe like government? Because as a professor, you probably apply for government grants. You have to apply to interact with people that control the money and that may not have a full understanding of what's going on. So like, I guess can you like describe the relationship between you and maybe higher ups or just, I don't know, other opinions in general?
Yeah, I mean, at the end of the day, the money that pays for the work I do is taxpayer money. So I do think about that. You don't pay any tax. I do think about that a lot, and and I think try to be responsible with the money that I'm given, and I try to spend it in a way that, as long as I'm honest about the work we're going to do, and then as long as these agencies come up with robust systems for evaluating what is high priority and what's low priority, then if I execute on that, then I think all parties, in general, can be agreeable that that's a good use of funds. Mm-hmm. Science is expensive, and I think that it is tough to explain quickly why that's so important, right? Like sparking the imagination, increasing human knowledge, major discoveries coming out of places you would never expect. All that stuff can seem a little intangible, and it seems like it's very easy to forget for people who aren't in it and practicing it all the time. And so, you have to kind of remind people that, like, well, that MRI that caught your breast cancer early, that came from a physicist trying to understand the spin state of the nucleus of helium, right? And so, that
years of
those
research
things
building up to
that you would never know that. And so there's countless discoveries like that, and I think there's always a balance of, like, we love to know more science, but at the same time there's a limited amount of funds, and they have to go to other things like defense and education, and roads and bridges. And so it's always a balance, and we'll advocate for ourselves, and they'll advocate for their programs, and hopefully there's more science in the future. But
right. So if funding wasn't an issue, what's one instrument or piece of equipment or material that you would invest in?
Lasers.
Yeah, honestly, that's kind of where my first thought went. I was spoiled in that my graduate lab was very instrument heavy, from years and years of amassing instrumentation. So we kind of had to pull it off the shelf and build whatever you wanted to do that day, which is really fun as a tinkerer and somebody who was big into Legos and stuff when I was a kid. It was fun to just, build things on the fly. But I don't know what I'm in a very practical phase of, like, instrumentation where I'm, like, trying to get little things that we really need. Not little things, but, like, recently, like, we got a new liquid chromatography tandem mass spectrometer. So it's got 2 mass spectrometers, so you measure the mass and then you can break the particle up into pieces and measure those masses, and that gives you some idea of structure. And that was, like, huge. It's an amazing capability. Like $350,000, $400,000, but but very, very cool and very useful. And so more mass spec capabilities would be great. More spectroscopy, EPR would be very helpful.
EPR is a
electron paramagnetic resonance. It's a spectroscopy technique. It's kind of like NMR, but for electrons, not protons.
Oh, okay.
Or a nuclear spin.
Okay.
Electron spin. So.
Interesting. Yeah. Okay, so I wanted to ask, because we were talking a bit about your grad school experience and all that, and you were talking about most of it being dedicated to essentially this, like, enzymology research, but you were saying that you started as a physical chemist by trade. So I was wondering, what did you mean by that, if most of the work you did in grad school was enzyme focused?
Yeah, so there are different people that work on enzymes from different lenses, and so some people study enzymes that are interested in the chemical reactivity in terms of, like, the chemical substances that can be acted on by the enzyme and that are produced by the enzyme, right? So that's a very chemistry focused, molecular focused.
Or the mechanism?
Mechanism becomes different, so then it can be, what is the chemical structure of the transition states, for example, or the transition state. How do I design inhibitors to target that transition state? It's a very medicinal chemistry approach to enzymology. Can also be in a mechanistic approach to enzymology. And then there's another, I think, class of people who work on enzymes who are like, how do these things even work in the first place? Like, at the end of the day, what you're doing is you're lowering the barrier for that reaction by, massive amounts that can accelerate reactions, eons, from what they would occur without an enzyme. And that field is spent a lot of time, and they still are somewhat active in debating how does an enzyme catalyze a reaction? Like, what is the origin of that physical process? And then what are mechanisms, and what are distinct chemical steps in the mechanism? So my connection to this during hydrogenase was, this enzyme is sort of the simplest case. It's acting on electrons and protons. It has 2 substrates that it combines into molecular hydrogen, and there's a phenomenon that's a fundamental chemical event known as proton-coupled electron transfer. So sometimes the movement of an electron and proton can become coupled in very interesting ways, and so they can move as a sort of single unit.
And that gets really interesting because we typically think of the proton as being very, very heavy, so it moves like a classical particle, and the electron as being very, very light, so it moves like a quantum particle, and it can tunnel and move over long distances with, no discrete, sort of trajectory from one state to another. It's here and then it's here. And so when those two particles couple, you can get elements of quantum and classical behavior of the system as a whole. So that was like the physical chemistry connection to me, and we discovered some of that proton couple electron transfer and proton tunneling in hydrogenases.
So even though you were working on enzymes, a lot of the theory behind it and what you were studying was very physical chemistry focused.
Yeah. Yep.
Wow. All right. Interesting. So what was it like for you to transition to being a professor from coming out as a grad student? You just finished grad school or postdoc, all that, and now you're becoming a professor. You have to teach classes. Like, what was that transition like?
I mean, it's if you're like me, I think I can't say I'm good at it, but I like having lots of things to engage me. I like having a lot of hats to wear throughout the day. So sometimes I'm a mentor, sometimes I am a grant writer, sometimes I'm a teacher in a class, sometimes I'm part of governance of the university in terms of committees and things like this. Sometimes I'm just an audience member in a discussion about science. So that's fun. It's a lot of different things, and being like right on the ground with the science happening right next door, or in my own hands from time to time, is really fun. The specific time that I've been a professor has been quite challenging, just because of logistical and personal reasons. But the job itself is very fun, and I've really enjoyed it.
So was teaching kind of a big component of going into that career for you? Did you have a lot of experience in that before? Is that kind of like a side thing? How important is that part to you?
Actually, I wasn't. I mean, I knew teaching was part of, obviously, a critical part of being a professor, but the thing that attracted me originally to it was like sort of being your own boss and being able to define what projects you work on. And as long as you can convince somebody to fund you for it, you can work on it, right? I don't have to work on this protease that Merck wants to work on. I can work on whatever I want. And so that was the appeal for me, was that research. But the teaching has become a very rewarding outgrowth of being a professor that I wish was communicated to me a little bit more effectively, because I would have took it more seriously and prepared myself better for it when I was entering. The last time I taught before I taught here at UCSB was during the first year of my graduate education.
Wow.
So TA?
Yeah, as a TA.
For Gen Chem?
No, I taught a physical chemistry lab course, just because I had taken some grad courses when I was an undergrad, so I had some preparation to teach an upper division course.
It's kind of like a tough class for a first-year PhD student to TA for.
Oh, I loved it. It was great. Yeah, it was a lot of fun. But yeah, no, I mean, like, one, teaching, but then I think the most rewarding thing is like seeing the final product, like seeing students go off to grad school, med school, and saying like, I'm actually going to work in biochemistry, like, like your class was like really great, or, I feel like I'm really prepared to take the MCAT, I'm really excited for med school, going off to do these, wonderful things, which is great. And then also, because I teach metabolism, I get to see the students' faces when I introduce them to like ATP synthase and like crazy, like how crazy biochemistry is. And I tell my students at the beginning of biochemistry, I say, this is going to be the coolest class you'll ever take in your life, because all the chemistry you've learned here, now it's like going to be put on steroids, and it's going to be crazy stuff that's been evolved over billions of years, and you're going to see some stuff that'll blow your mind. So
it's really cool. Yeah. So like, what career would you have chosen then if you didn't ever pursue STEM?
Professional thief.
Now you see me. Now you don't.
I have a lot of interests outside of chemistry. I mean, I like journalism. I'm could have seen myself being a journalist.
That was we made bets before this. What he was saying, I said journalism.
Yeah, he did.
Okay.
I said chef. I said chef.
Yeah.
was a
Chef,
good
I don't
guess,
think
too.
I could have handled. I think there's a lot of, well, maybe I could. I don't know. But yeah, I think
Should put money on it.
economist.
Okay.
Yeah, I don't think I could do something in sales. I think I'd not enjoy that.
Okay.
I don't think I'd be a
Journalism,
good
economist.
CEO either. I mean, like, you're kind of a mini CEO as a professor, but it's like with a bunch of other CEOs. You're still like gotta work together.
Yeah.
Yeah, like branch managers.
Yeah, I think if I was given unlimited power, I would be corrupted.
Interesting. Okay, so then I guess there's that, and then what other field within STEM would you, if not chemistry, biochemistry, would you have seen yourself pursue?
Yeah, I loved physics. It was like the first, like what drew me to science in the first place. But you know, and my physics friends don't listen to this, but it doesn't seem like there's a lot of like low hanging fruit left there. That physics has advanced a lot, and the systems that they need to study to be stimulated are extremely complex and extremely challenging. So it's like, you know, looking for, you know, trying to be the person after, you know, Einstein and Oppenheimer and all these other people and Feynman and, you know, et cetera, to discover the grand theory unifying
Everything.
all physics seems tough. Or, you know, studying weirdly intrinsically chaotic and disordered systems and then trying to apply physics principles to these weird disordered systems that are high complexity. So yeah, those, I think, you know, I'm interested in them, but I don't think I could have done a career. I think probably maybe neuroscience, brain science would be an interesting area because I think it touches on a lot of like intrinsically self, you know, aspects that would be fun to ruminate and think about, and there's a lot of space to fill in that area. So how the brain functions is still a pretty open question.
Yeah, and like the chemistry behind like a lot of.
Yeah, chemistry too. But you asked me for something different.
That's
so
true.
I am.
That is true. That is true.
Well, he was hiding the chemistry in that.
Yeah.
answer.
Yeah, no, exactly. Subliminally saying that he wanted to look at the chemistry of the brain.
Yeah.
All right, fair
It's
enough.
really cool.
I guess we could ask some UCSB specific questions.
Yeah, for sure. We
Since
can
are
transition.
here at UC Santa Barbara.
So yeah, what
So-
drew you here in the first place?
I got an offer.
I said I was gonna.
Yeah. So yeah. Full disclosure, I had two interviews. I had one here and one at Yale, and then I didn't get the offer at Yale, and I got the offer here. So
Would you have taken the offer at Yale?
probably not. Yale was a very insular department in that it seemed that it was kind of like you're going to be on your own and you're going to sink or swim, and then when you get tenure, we'll talk about you doing something in the department.
Oh boy.
and being a member. But it was a beautiful campus. They were great scientists there, and it would have been fun. I think it was a little bit less
Camaraderie
Welcoming.
and collaboration, and so I really like my colleagues here and the environment.
Yeah, for sure. So yeah, I mean that's one of the things that I've been curious about, because I remember hearing some of these just differences in the scientific culture, both from different universities and especially between West Coast, East Coast, like other countries. So can you say anything about that in terms of the culture here at UCSB on the West Coast versus other parts of the country or the world? How is it different? What do you like or not like about how it is here?
So California gets high on its own supply. To put it into a phrase, we get a lot of Californians that come to UCSB. Obviously, it's a state school, but people don't want to leave California, so they will stay in this area despite getting offers at better schools, despite other things.
Are you from California originally?
No. So we get a lot of people that are from California that want to be in California that are here, and so at least UCSB is very much a reflection of Californian people, and every region has its own sort of like, stereotype or some sort of like,
Mm-hmm.
mean personality type, whatever that is. And so it is a much more laid back, I think, place. It does have a lot of that like sort of work hard, play hard, seeking adventure, grandiosity to it. And I went to undergraduate at Washington State, so in the Pacific Northwest. I went to graduate school at Emory, which is in the Southeast in Atlanta. I went to do my postdoc at Harvard and MIT, and so in the New England area. People are different everywhere, and different places have more, cultural connections to other places. So, for instance, Emory was there were very few people from Atlanta that were at Emory. It was people from all over the place. So it was a very dynamic place, and it didn't feel like, at least in the science department, that you were like in the South in the college. When you left that, you did feel a little bit more like you were in the South. But Atlanta is a very metropolitan city, and it's got a lot of business, so there's people coming from all over. New England felt like New England. A lot of people from New England, and it moves fast, and it, and it talks fast, and it doesn't have much patience, but they do very cool things, and it's it's got its own cultural things that are great. So every place has its own energy, its own vibe, but California definitely has a big impression on UCSB for sure.
Where in your career were you when you got your tattoo?
Which one? These I got essentially as like a wedding present for my wife and I, an anniversary present.
What is it?
An oyster and a shucking knife.
So why a shucking knife?
Because I like oysters and I shuck. But the bigger, I guess, background was we got married in Maine, and we really liked Maine, and Maine is very famous for its oysters and lobster. So it was a kind of a homage to that. But in grad school, I'm a very big college football fan. And so, if I was going to take some time off on the weekend, I would definitely take it off on Saturdays to watch college football. And I would go get a dozen oysters at like a local oyster farm that I really liked. And I would just sit on the couch and I would shuck oysters and watch football. And it was very fun.
Oysters and football is a crazy combination.
It is. But it felt very fancy because I was this poor postdoc, but oysters are pretty fancy food. But if you go to the farms, they're pretty cheap. And so it felt very fancy. I felt like I was living high.
The life hack for you.
Yeah, life hack.
Nice. So I guess going back to sort of your experiences in different regions of the country, what were some of the main differences you noticed in the culture specifically and how they do science?
Sure. I think that, New England, there's at least in my experience, there's and especially at places like MIT and Harvard, there's like a competitiveness that can stimulate a lot of great discovery, but it can also like lead to some elements of toxic workplace where it feels like people are competing against one another and not working together and not supportive.
Damn it, John already found this. How can you not find this?
Yeah, or like this is not, I don't think, the norm by any means, but like you hear stories about people poisoning other people's experiments. These kinds of things that.
Wow.
And that's not to say again that this is like all of it or by any means, but there is a competitive pressure at MIT and Harvard where it feels like it's a zero-sum game. Like if somebody else succeeds, it's going to come at the expense of me because they're going to get more time with the advisor. They're going to get a better letter of recommendation at the end. And so I need to be as successful as them, or I need to hold them back. Anyway, here it seems like it's a much more like everybody's trying to float. And
lift each other up.
Emory was like that as well. It felt like everybody was kind of trying to succeed and weren't trying to hold anybody back. But the pace is different too, right? So one of the complaints that a lot of young professors get when they come from Harvard and MIT is like, oh, my students don't work as hard as I thought they would. And the people at MIT and Harvard work really, really hard, probably too hard. That there's a healthy work, and it also is selected for a very specific, breed of human being that's willing to be in that environment. So, people have a different relationship to work and life, and that's totally fine. There's regional differences to that, but there's also just some scientific differences too.
We do have a question that we would like to ask all professors at
Sure.
the end.
Yeah.
is how would an undergraduate go about getting research or getting experience at UCSB?
Yeah, good question. So I think that there's probably a bunch of like sort of boilerplate answers that most people probably know, but are worth articulating, I guess, especially since this is the inaugural podcast. So there's the Faculty Research Assistance Program, FRAP, which is an online portal where faculty can advertise research projects that they're interested in undergraduate support for. And so you can peruse those to get some idea of what projects are available. If you apply for those programs, that provide some funding for the faculty. It's not much, but it is some. So there's an incentive there both ways. Unfortunately, because of the way the system is set up, oftentimes faculty will create the position after they already have a student that they want to assign to it. So some of those positions, maybe a large fraction of them, are already filled. And so, yeah, I don't know what the success rate is in other departments, but at least in the chemistry department, it seems like most of the advertised positions are already filled. But they're still worth a try. The second is to just ask people. So in particular, if you have colleagues who are undergraduate researchers, like reach out to them, see how they did it. If you have a graduate TA, you can reach out to them. They're oftentimes a great bridge to a research position because they have a very close relationship with a faculty. And so they can say, hey, I had this student who got an A in my, Gen Chem lab, and we should keep an eye on them. And their next year, they'll be, probably prime time for undergraduate research. And then I would say the last thing is, personally for me, students can use my website to get access to the right information that I want to see from an undergrad. And it also shows some effort on your part to invest in, your own research. It's not like you just went through every faculty and sent them the same email. You actually read what we do, you express some interest in it, and I give specific guidelines for what I want. So I want a CV or resume, and I want an unofficial transcript. And so if you don't attach those things, I have a pretty strong idea you didn't read the website, and therefore I'm a little less inclined. Mm-hmm. The last thing I'll say is that, undergraduate research is important, but there are ways to, if you want to move into a graduate program, it's not absolutely necessary. And I would strongly encourage people who are perhaps, maybe struggling with grades to think about that as a much higher priority than getting undergraduate research. At the end of the day, for better or worse, and probably for worse, there is a number attached to your degree, and that number is looked at by everybody. And so giving yourself the time and space to really focus on your academics is going to be the most important thing you can do. It's what you're really paying for at an undergraduate institution. And then the research should be on top of that. So that is one thing that I tell students occasionally when I see students who, have transcripts that maybe, indicate there's been some academic struggles along the way, that I say, come back. I'm happy to reconsider this, but I think like the best effort and, best time spent right now is on your academics. And that's not a knock on anybody. Everybody has a different journey through college, and some people working 3 jobs, and it's hard to study, for a really tough midterm, and some people have all kinds of reasons for difference in grades, but that's just something that I think should be top of mind, and then research is in addition to that. Lastly, and I'm hoping to incorporate this into our curricula, is that there is not enough room at UCSB to give every undergrad a research experience, and in fact there's not enough to give every undergrad who wants research experience. We just don't have the capacity to do that. You need to have some mentorship, and faculty are already spread very thin, and there are many, many less graduate students than there are undergraduates, so you can put them 2 and 2 together, and there's not enough. But what I am trying to do is to try to incorporate into our lab courses some elements of research. So if you have a lab course, then you could, instead of just learning a technique, you could ask a question. And then the techniques are learned along the way, but they're in service of a research question.
And you learn some of those same skills.
Exactly. And so you learn the same tools, but you learn them in service of a scientific goal that is really where research is different than the typical lab class. Typically you say, okay, well, now you're going to titrate, so find the light pink and write down the volume, and then, and instead say, like, there's an unknown acid here. How are you going to find out what that, acid is? Like, this is a forensics problem or what have you. So that creation of a little bit more research is tough. It takes curriculum development. It takes time and effort from faculty, but I think that with some time and effort, we'll get there hopefully with our upper division lab courses.
Yeah.
Right. So aside from just getting into research or, putting yourself out there and finding a position, how would you sort of recommend undergraduates navigate all the different research opportunities that are out there in terms of figuring out what kind of experience they want, when is it the right time to maybe move to a different lab or a different project, figuring out what you really want to pursue in terms of research?
Yeah, it's a good question. So I would say I would never turn down an undergraduate who said, I would really like to come to your group meeting and just hear a little bit about what your group is doing. There's no reason why that shouldn't be allowed. There's nothing secret about the research in my lab. We're happy to have new people, as long as you're not like being obnoxious and like what's an electron? Give it a little time to soak it up, and we're happy to answer questions maybe a little after. But so that's a good way to get kind of the feel for what that lab is like, at least just in the conceptual way. And then if you know some of the undergrads, usually they're posted on people's websites, not always, but oftentimes if it's usually a sign of a research advisor's interest in undergraduate researchers, whether they put them on their website or not. So if they're on the website, you can reach out to them directly and just say, hey, like, what's a day in your life? Like, I'd love to, buy you coffee or buy you, whatever, yerba mate, or I don't know, whatever. But this is my water glass. But anyway, you can get some like firsthand account there, and that be wrote in. And most, I think, undergrads are pretty open to communicating back to undergrads that are interested in seeking out positions. Once you're in a position, if you want to change, that usually is something you want to handle delicately, because it can be very frustrating for a faculty and graduate student to have spent a lot of time getting up to speed, and then you say, I don't think this is for me. It's like, well, now the value in return is usually paid off only in the end for undergrads, right? There's an initial phase where there's a lot of time invested in them, and getting them up to speed with the research, getting them up to speed with the project and the goals, and making sure that they can navigate space in the lab alone and design their own experiments. And then once all that is in place, then they start doing things that are, really like kind of emergent value. So it's a long-term investment. So you just want to do your due diligence before you join a lab, if at all possible. Now that there are times where this, doesn't work, and that's fine.
You start working there, you realize that it wasn't maybe what you expected, but I guess you're saying the earlier, the better. And
the more due diligence you do, the better, right? If you're thinking about two labs and you're kind of right in between them, don't feel like you have to commit. Give it a couple months, and go to the group meetings, talk to the grad students or undergrads. Think about it a little bit more, read some papers, do some introspection.
Yeah, and definitely give a heads up if you are going to.
Yeah.
So kind of related to that, how picky do you think you should be with your undergrad research experience in terms of the labs, the projects?
I don't think it needs to be that picky. I think, what I'm looking for, so it depends on what you want to do, I guess, to some extent. If you are just interested in seeing what research is like, and you kind of are thinking about just getting a job after this, but you're maybe curious about research, I don't think it really matters. I think you can go almost anywhere and get the idea, get the feel for it. I mean, granted, there are certain places that are better than others, but if you're pretty confident you want to go to graduate school and you want to do research, then it becomes much more important. But again, I think at the end of the day, what I want to see out of the researchers that I train is not that they're experts in redox biology, it's that they're good at asking critical questions and designing experiments. And so if you trained as a really, really good organic chemist, but then you want to go into molecular biology or whatever, as long as you have invested in trying to design good experiments and to how to organize your work and how to do these kinds of things, you'll be able to figure it out.
Yeah.
Right.
So I think for graduate school, we often have a statement where you have to say, like, what did I do? What made me want to do this, and what prepared me for it?
Right.
And that's where, I've had people that have, purely bio backgrounds or very hardcore physical backgrounds that can explain how that research experience relates more generally to research as a whole. And so that's a place where you can say, hey, I don't have experience in your specific science, but I'm interested in your science, and so let me explain how I think about science regardless of the discipline, just how I approach problem solving in this, and what I learned. From this long set of experiments, I learned that perseverance is really important. Sometimes it takes a long time to figure a problem out. And I learned that details are important because I didn't read this previous paper that explained that you have to add DMF to the reaction. The little caveats that you can pull out to say, this is what I learned and I'm going to carry this going forward is attention to detail and perseverance and hard work.
So even if you end up going into pursuing a graduate program that's somewhat different from what you were doing.
Yeah.
Okay. So I guess if there is an undergraduate student who's doing research and then they have a good research experience, they're already at that point, like you said, where they're kind of trained up and they can start doing stuff, but then let's say they look at graduate programs that aren't in that exact field, is it worth maybe sticking it out in that lab, or should they try to find something more specific to that field? I guess that's something I think a lot of
you're going to be doing
it's
actually kind of the same story with graduate school. It's a little bit more pressure, but it's similar.
Yeah.
The most important thing to learn is problem solving and critical thinking. And so as long as you can articulate that and you can use it moving forward and you're willing to do the work of learning something new, you'll be fine anywhere. So I had an undergraduate student, one of my first undergraduate students, who was an exceptional biochemistry student and really wanted to get into cancer biology and got accepted at Washington University Cancer Biology and is doing great. And if you're willing to do the work and you're willing to think about research as a problem solving and exercise and a scientific method exercise, then your skills will be very portable to other disciplines.
Right, and I guess that goes back to what we were saying earlier about developing those problem-solving skills, and then
there are certain skills that are harder to pick up than others, and so there's obviously barriers to certain transitions, right? If you want to go into a pure biology lab that's doing tissue culture, and you don't know how to do tissue culture, you're going to have to learn it, and it does take time and it takes perseverance. If you're willing to put in the work, though, I'm almost certain you can do it, and and you can pivot.
And you think those programs would still consider you just as much if you didn't come from a background already knowing that stuff?
Well, there's only so many slots, right?
Right.
And they have to consider that. So it's different for every discipline. But I would rather have somebody who says, I understand the value of hard work, perseverance, and attention to detail, and approaching each experiment with a level of I don't want to say risk, but a level of chance and opportunity. I'll take that person over somebody who says I'm really, really smart in biochemistry, any day, because I think you can learn a lot, and as long as the attributes are there that help, that are sort of foundational to the scientific knowledge. Scientific knowledge doesn't get you anywhere. It gets you, in principle, if you have the other skills, it gets you to ask really smart questions. But the scientific knowledge, without the work ethic and without the perseverance and all that kind of stuff, that it doesn't go very far.
I can't wait till somebody listens to this podcast and on their resume they put, my skills are hard work, perseverance, attention to detail.
Flattery will get you everywhere. I won't turn it down. I think there's that's the case for a lot of things, right? I mean, you hear all the time, investment banker, wants to hire a farmer and not an intern coming, in from another hedge fund, right? It's like, that person works really hard and they're hungry and they're probably going to figure it out, and even if they take a little longer to get to the place where the other person would be when they come in, they'll go farther. Yeah. And so I had this happen to me. I was, when I was young, I moved a lot, and I was in a school where I had a band class earlier than another school that I moved to. So I was already like a a pretty decent trumpet player by the time I was moving to this new school. And the new school, they were just starting their band class, so no one had ever played an instrument before. So I was first chair, day one.
Nice.
And it was like, yeah, this is awesome, whatever. So I didn't have to practice because I knew how to play everything they were doing that whole year, and I could just show up and play the music, and it was fine.
Oh, that's great.
But by the end of the year, I was second chair because somebody, below me was hungry and saw me as first and worked. And I laid back and was like, oh, I'm really good at this, and I don't need to learn anything.
Not complacent.
And there's and so
It's literally just like whiplash.
yeah. So
Yeah.
It's very important.
Yeah, I think.
It's probably all we have time for today.
Yeah, it is probably all we have time for. Thank you so much
Yeah.
for being our inaugural episode.
Yeah, it's
thank
been a
you
lot of
for
fun.
Sitting down with us,
Yeah.
and thank you to whoever listened to this.
Yeah.
Yeah,
Thank you
well,
to our
we'll have to,
listeners.
get a pH strip because this was anything but basics.
There you go.
And that's your dad joke of the day.
That's my dad joke.
That's your dad
I'm
joke.
out. Mic drop.
Yeah, that was Brandon Greene. I'm Nathan. This was Liad, and we thank you for
My
listening.
name's Leon. I can introduce myself. Thank you.
Okay, well, we'll cut that out. This was Brandon Greene.
Kidding,
My
I'm
name
just
was
messing
Nathan.
with you.
All right. Yeah, that's it.
Signing off.
Signing off.